Okay, so we're looking at the next part in chapter 6.1, which is talking about angled launches. Okay, so yesterday we talked about things that were projectiles going directly horizontal, right? Now we're adding some angle to it. So something like this. If this projectile is launched at 2 meters per second, and we were to say that this was a 55-degree angle, right? And I want to know 3 things about this, the 3 details about this object. What is its hang time? What is its maximum height? And what is its range? And this is what the problems, numbers 4 and 5, are asking you. Can you find these 3 things? And the piece that I gave you all, the handout, is equations that look like this. These are the same equations that are over here on the whiteboard, right? There's no difference. I'm just showing you how they apply to these specific situations. So if we're talking about hang time, we're using that VF equation, just like we have over on the board there. We changed it to Y because we're dealing with up and down, right? But in this case, to find the hang time, are you comfortable, as soon as this thing is launched, the initial velocity in the Y is 0. And when it lands, it's also 0, right? Because it's gone up and it's come back down. And in that whole period of time, the velocity went from 0 to 0, right? It sped up, it slowed down, but at 2 ends is 0. So we can make both of those to be 0. And my acceleration is simply just the acceleration of gravity, right? So therefore, we can rearrange this equation by getting rid of the other pieces to be that time equals 2 times Vy in the I, the initial direction, right? The velocity in the Y, right? So remember, here's our velocity, right? I'm saying we can make an X component and a Y component, right? So we're only going to be using the Y component for this hang time, not the X component. So time is equal to 2 times velocity initial in the Y divided by G. That's it. That's breaking down this equation, getting rid of all the pieces that are 0. For maximum height, I'm going to use the exact same equation as what we did for hang time, but there's a little caveat, a little thing you got to make sure you remember, that you're only using half of the hang time. Because if I were to toss up this marker, right, into the air, the time it takes to get its maximum height there is half of the time it takes to go up and down. Does that make sense? The instance would be if it didn't start and end at the same height. In other words, if I'm going off a cliff where I throw it up and then it goes down below the cliff, that would not be the same. You're correct. But if we're talking about a nice parabolic, then yes, it would have to be the same. So therefore, when I plug this in, the time I put right here has to be half of the hang time, not the full hang time. And then last but not least, range, just like we've been doing before. Range is just distance is rate times time. But remember, it's the X component of the range. So let's give this a shot here. If I have a soccer ball that I kick at 16.5 meters per second, or maybe Richard kicks it, because I'm not sure I can kick it at 16.5, and at 37 degrees above the horizontal, I want to know what the ball's hang time, maximum height, and range are. So let's do hang time first. Again, because we need time to find the other 2, so let's do hang time first. Again, my equation I'm going to use is T is 2 Vyi divided by G. So first, I need to take my velocity, that's 16.5, and I need to find its Y and its X. So how would I do that? If I want to find X, which is X? Is it adjacent, opposite, hypotenuse? It's adjacent, right? Okay, so I'm going to use 16.5 times, is it going to be cosine or sine to find X? It's going to be cosine, because cosine is adjacent. cosine of 37 degrees. Help me out. I don't have my calculator here. I'm not coming prepared with these numbers. So let's pop in together. See if you can beat me or I can beat you. 37 cosine times 16.5. I get 13.2. Good? So my x is 13.2 meters per second. My y is going to be 16.5 times the sine of 37 degrees. So my y is going to be equal to what? 9.93? Is that what we got? Not that I don't trust Casey, I'm just asking. 37 sine, no, that wasn't right. 37 sine times 16.5, 9.93. Perfect. Meters per second. Okay, so for my hang time, since this is my equation, right? Time is 2 times velocity y initial divided by g. Which am I going to put? T equals 2 times which of these times, or which of these velocities am I going to use? I'm going to use the y. Exactly. Because we're dealing with it going up and down. 9.93 divided by 9.80. So therefore, my hang time is going to be what? Let's do our math here. 9.93 times 2 divided by 9.8 is 2.03. 2.03 seconds. That's how long that soccer ball that Richard kicks stays in the air. Which makes sense. He kicked it fairly low on an angle, right? He didn't kick it way up in the air. It's fairly low. A striker's strike. All right? All right. I roll it down a bit. If I want to now find what's the maximum height that he sends this ball, well, I'm going to use this equation, right? My regular distance equation. But again, I'm only going to use half of my time. So, YF equals, my initial is 0, right? Initial is 0 plus Vy, the initial velocity in the y. So again, I'm going to use 9.93 multiplied by the amount of time, but it's half of this, right? So 1.015, I guess, is how we can do that. Plus 1/2 AT squared. So, I'm rolling down here. 0.5 times gravity times 1.015 squared. Now, here's my question to you. This velocity that we've given this ball, right? This 9.93, we're calling it positive, right? What direction is the ball going? Is it going up or is it going down? As we're moving to get to the maximum height, it's going upward, right? Which way is gravity going, my friends? It's going down. So therefore, I have to have this as a negative acceleration. Does that make sense? Because it's slowing it down, right? It's going to get to that maximum height. Otherwise, it's going to be accelerating it faster. Gravity's pulling it upward. We know that doesn't happen. Okay, so let's do our numbers here. YF is equal to, I find it easier to actually do these separately, 9.93 times 1.015. That gives me 10.0789. And then I'm doing 0.5 times 9.8 times 1.015. And I get minus 4.9735. Subtract those two numbers, 10.0789 minus 4.9, and I get that my YF is equal to, is equal to 5.1054. So we're going 3 significant digits. So 5.11 meters. That's how high Richard's kick gets. So 15, almost 20 feet off the ground. Makes sense. Again, he's kicking it reasonably low, but he wants to get it over the defender. That makes sense. Okay? He's there. He's got it. I got no doubts in Richard's ability. Last but not least, I want to know how far did this thing travel? In the X dimension, what's its range? How far did his kick go? Okay? So this is my simple equation, right guys? It's just distance is rate times time. So therefore, my range is equal to x equals to, what's my velocity in the x? It's the first time I'm going to use this 13.2, right? So I want to make sure you hear me. For my maximum height and for my hang time, I'm using the y velocity, the y component of the velocity. Whereas now, in my x, to find my range, which is x dimension, I'm using the x component. So 13.2, I'm multiplying it by the amount of time Richard keeps the ball in the air, 2.03 seconds. And I do my math. 13.2 times 2.03 equals 26. 26.8 meters is the distance that Richard kicks the ball. A good, decent strike, getting the ball down the field. And hopefully into the back of the net. Are you with me, my friends? So in the problems you're given in your textbook for numbers 4 and 5, they're using these same equations, right? I'm reviewing here. Stay with me. You're going to break the velocity given into its components, x's and y's, right? You're going to use our equation for hang time, which again is the same equation as this YF equation we've been using over and over again. It's just that my distances are 0. It starts at 0, it goes up, it comes back down, it ends at 0, right? So there is no y height that's going on. There's no displacement that happens. My velocity is going to be the y component divided by my acceleration, which is going to be gravity. For maximum height, I still use that maximum height equation, that same distance equation we've been using since chapter 3. Excuse me. And then for my range, my distance is velocity times time, same equation we've been doing since chapter 1. Are you with me? Good. Thanks for letting me record here.